All right, so let's see if we can put a wrap on this derivative of exponentials and logarithmics unit, lesson 9 out of chapter 3 in our book. We're going to start with just doing one more example of what we've done with the exponential. So this problem is 3 to the e to the 5x minus 1. So we would start that. We can put the 5x minus 1 certainly on one arrow because we know what the derivative of that is. The next place that goes is in the exponent of e, so that gives us an e to the 5x minus 1. And then we do 3 to the power to take care of that. So our derivative of 5x minus 1 is just a 5, no place to put that x, it was just linear to begin with. The derivative of e to the power is e to the power, and the 5x minus 1 is going to drop into there. And the derivative of 3 to the power, we figured out, was natural log e times 3 to the power, and that power is e to the 5x minus 1. So again, the derivative of an exponential will always have that exponential in there. Again, if we put all of these things together, remember this 3 is a base, but we have a 5 times the natural log of 3 times an e to the 5x minus 1 times a 3 to the e to the 5x minus 1. All of those things multiplied together. And if that was f of x, then this is f prime of x. Again, what that looks like, I don't know, the double exponential kind of thing right there, I would assume climbs insanely fast. But let's take a look then at logarithms. All right, so derivative of natural log. We'll start with natural log. It seems like the natural thing. Bad pun, unintended. It seems like the way to go here is with the natural log because everything worked out so well with base e on our derivative. So base e in a logarithm maybe would make things a little bit cleaner as well. So what we're searching for is if we put something into a natural log, then what will that derivative be? And so let's take a look kind of graphically here. I thought I had that pulled up. Let me pull that up. So here's graph of natural log of x. And we're going to use the numerical grapher here just to give us an idea of what we think that might look like. So if we see that, we might grab some points along the way. This is the point 1 comma 1 is on the derivative. The point, if we pulled some other ones here, let's see, the point, it looks like, oops, harder to do this from up here. 4 comma 0.25 was on there. All right, so kind of back over. All right, so to try to see what's going on here a little bit better, I put a table in here and recorded the values of the derivative for several different inputs. And we can see those lining up on the derivative graph there. And so when I put a 1/2 in, I got a 2 out. A 1 gave me a 1, a 2 gave me a 1/2, a 3 gave me a 1/3, a 4 gave me a 1/4. It would appear that the derivative here is just the reciprocal function. And so if we try that, let me go down in here and I'll just try to enter the reciprocal function in there. So 1 divided by x, and we see that that gives us the graph. It definitely gives us the part over here in the negative quadrants, in the negative x-axis. as well, but that's not part of the domain of natural log in the first place. So it's not part of the domain of the derivative of natural log. But the gist of that, what we've gotten down to, is that the derivative of natural log is the reciprocal function. Okay. So we can add that now to our list of tools that we can throw in the middle in combinations with other functions in product rule, quotient rule, chain rule, and come up with derivatives of those things as well. It does leave us a little bit in the question of, okay, what about the other ones? What if we had something that looked like log base 8 of x? Okay. If we want to do that, well, if we remember, we can always change bases, and one way to do that change of base, if we rewrite this logarithmic into its exponential form, we could call it 8 to the y is equal to x. And if we hit each side with a logarithm, we get y times the natural log of 8 is equal to the natural log of x. So y, which is this same y, is equal to the natural log of x divided by the natural log of 8. So it again just becomes a vertical stretch or compression depending on what that value comes out as. Okay, we know natural logs can also be negative, so there could be some kind of reflection coming out of there as well. All right, so, but that would only be for a log of a number less than 1, and with base of a logarithm less than 1, we don't come across that very often. Not impossible, but don't very often come across those. So if we wanted to do the derivative of this, we could say that the log base 8 is equivalent to a two-step process of, first of all, taking the natural log and then dividing by the natural log of 8. And so if we want the derivative of that, well, our derivative of natural log we figured out was 1 over, and this is essentially, this is just multiplication by a constant, and the constant is 1 over natural log 8. And so our derivative, if we started here with an x, we get an x in there times 1 over natural log 8, and so this is 1 over x times the natural log of 8. I'll probably write it that way so I'm sure that I don't mistakenly assume that the x is inside the natural log. But this then is the derivative of the log base 8 of x. And so if we wanted to generalize that, we could say if we have a log base b, any base, then its derivative is going to be 1 over empty set of parentheses times the natural log of b. And so we'll try that out in some places. I do think I have an example down here, or actually that's not even an example. Maybe there's one on the next slide. There's not. Let me stick one in there. Let's say we had y equals x squared times the log base 7 of sine 2x. Okay. Well, first of all, we recognize there is a product rule. The x shows up in more than one place, and there's a multiplication. So we would need first times the derivative of the second. The second is more complicated, so we're going to come over to calculate the derivative of this with a chain rule. Start with the x, multiply by 2 gives us a 2x. That goes inside of a sine, and now we have a sine of 2x. And then we take the log base 7 of that. So derivative of 2x is just 2. Derivative of sine of something is the cosine of the something, which in this case is the 2x. The derivative of the log base 7 is 1 over the something times the natural log of 7, and the something in this case is a sine 2x. Okay? So putting that all together, we have a 2 cosine 2x over sine 2x, and there's also a natural log 7, so 2 over natural log 7 times that, which is the cotangent of 2x. So I'm going to have a 2 over natural log 7 x squared cotangent of 2x. And that is first times derivative of the second plus the second, which is our log base 7 of sine 2x, times the derivative of the first, which is a 2x. And I could do a little bit of rewriting there and factoring out some common things, but that's pretty much the gist of it. Probably all I would do is take this 2x and put it up in front of this. As a simplification, I don't think I would need to do anything else. So, it's an example of using the logarithms of bases other than e, which brings us to this interesting problem. Because if we look at this, we're trying to think, okay, it's the base is x, so that looks kind of like a power rule, except that the thing in the exponent is not just a number, it's a variable expression as well, so that looks like a exponential because there's a variable there, but it's only an exponential if the base is a number, so this is some other kind of hybrid thing that we probably have never seen before. Okay? But I promised you, you'd be able to take the derivative of anything. So, the approach we take is a technique called logarithmic differentiation. And the thing that we normally do when we have variables in the exponent, because they're very difficult to deal with up there, is we try to get them out of the exponent. And so and our tool for doing that is logarithms. So if we took a natural log on both sides, and we like natural log because it works so well with calculus, and we can write it in cursive, it's only 2 letters, so we can write it faster. We get natural log of y is equal to sine x times the natural log of x. And this now, with the help of implicit differentiation, which is why we did that before we did this, we can do the derivative of this expression, this equation. Natural log y, remember y is a function of x, so we started with an x and had to change it into a y, and then it went into the natural log. And so the derivative of y we call y prime. The derivative of natural log is 1 over something, and in this case what was at the beginning was a y. Okay, so looks like a 1 over y times y prime there. I'm going to move that off to the side a little bit. Say my derivative here is 1 over y times y prime. Over here now I have created a product rule that I need to do. So for the product rule is the first times the derivative of the second. Derivative of natural log x is just 1 over x, plus the second times the derivative of the first, which is going to be cosine. But I want this to say y prime. It would say y prime if I multiplied both sides by y. So if I took and multiplied by y on both sides, I'm going to get that y prime is sine x over x plus natural log x times the cosine of x, and all of that is times y, but y is, well, I'll split this into separate steps. This is implicit when our original one was not. I can do something about this y because I know y is equal to x sine x. So my y prime is sine x over x plus the natural log of x times the cosine of x times x to the sine x, and this then is my dy dx. The technique again is called logarithmic differentiation. We have to be careful to make sure that we've cleared everything out in front of this before we hit it with logarithms. If there was a number in front of there, I'd want to divide that over to be with the y. Or remember that when I put the logarithm on there, I'd have to change that into an addition before the sine x could come down from there. Okay, that is the idea of logarithmic differentiation. I'm assuming there will probably be some questions about that, but we're going to allow time for that anyway. So I believe that is the end. Yep, that's where I was going to stop with the lecture anyway.